Order.
This meeting is being recorded.
Recording in progress. We'll start things out with robot news. I saw the other day that this robot's name, the Boston Dynamics new robot, what do they call it?
Atlas, is that the one you're meaning?
Stretch. Boston Dynamics new robot Stretch has got a job with DHL. I just posted it in the chat there. $15 million investment in DHL. And this one's interesting because the gripper is a suction. Like that. It used to be kind of wonky. Hey, David Curtis. It used to be kind of wonky where the back end would go up and down, and they had it in some of their dancing videos. But now it looks a little more professional, and it looks like it's going to be rolling out a fleet at DHL to try and keep up with Amazon. And needless to say, the warehousing space for robotics is white hot. What else we got for robot news? More robot news out there, anybody?
Sure, I just read an article that says a six-legged robot will join the Winter Olympics to show its expertise in skiing without losing balance.
Six-legged?
Six-legged robot skiing. Okay.
That sounds like something Nick Donaldson would put together.
It was put together by Shanghai Jiao Tong University.
Hmm.
If I had 8 legs, it'd just be a toboggan.
It, if it was one-legged and it could balance, that'd be more impressive.
Well, you remember Nick Donaldson's Marauder at Robots on Ice, just that giant 8-legged spider robot. He actually got Intel to pay for that. I think that's $250,000 worth of robot. It's got like must have I don't know, 16 of those ginormous servos on it or something. But anyways, what else? Any more robot news out there? The Olympics is coming up on the 20th, I guess. Is that, no, it's the second week in, that's the Daytona 500 on the 20th. I think it starts on the 2nd or something like that, February. Any more robot news out there? All right, well, let's move on into club news. And in club news, next month, we're going to have Pablo Sobran doing the presentation. Pablo is the founder and sensing wizard at Impossible Sensing, and is also a research scientist at the SETI Institute. Let me get something in the share my screen again. I was trying to do a Microsoft Teams meeting with him this afternoon. He's over in Europe somewhere, but this guy, he's the founder and sensing wizard at Impossible Sensing and research scientist at the SETI Institute. So we're going to be talking about space robots. Any other club news out there?
Yeah, I'll make an announcement. I'm in charge of membership, collecting dues and that sort of thing. And even though we're not meeting in person, it's pretty important to support the club. Completely voluntary. You can come to all the meetings and participate in most things without being a member, but having a strong membership is really essential. Hopefully we'll get back to live meetings later in the year. Can only hope for that. So anyway, look on the HBRC homepage and look for the membership link and click on there and sign up. Would be appreciated. That's it.
Quick question, how do we know if we've paid already? Because I don't remember if I paid last year for this year or not. Is there a membership roster that's on the website?
I have a membership roster. I can send out a notice to the people that are paid.
Or
Just
more
pay it
important,
again.
those people that haven't paid yet?
Yeah, I'll put something up on the mailing list as well.
If you're not sure, just send Dan an email and he'll let you know.
Just send in $100 and I'll work on it.
Yeah. Hey,
Just kidding.
you know-
It's $10 a family. It's a good deal.
say, Mr. Mike, you were talking, who's it that's Makerspace that's opening back up again, that Maker Nexus?
Yes. They've been open all along.
So, but they moved, right?
Yeah, they moved a couple blocks away.
Okay, are you a member there now or not?
I suspended my membership a few months ago, so I am not. But I'll reactivate it when I have time to go back there.
Yeah, we want to look for a space, and moreover, even I think somebody looking for something to do. We kind of need somebody to head up the extracurricular events. Like if we wanted to go to something, I think there was the robots on ice, and you know we showed up there, but not so much as a club, but as a group of loosely coupled individuals, something like that. But maybe make a head of extracurricular activities that's local there. Until I can get my telepresence robot together and be there telepresently.
So I talked to Maker Nexus before I signed out there, and they were quite happy to host our meetings. They just need, I don't even know if somebody needs to be a member or not. So they have a room that is probably half the size of the alternate Google location. Not the one that was on Crittenden, but the other one. And then, of course, they have the whole makerspace right next to it with, metal shop and wood shop and 3D printers and long arm sewing machines and vinyl cutters and just even an electronics lab. They've got a lot of stuff there, and it's a much bigger building than it was before.
We sound like a perfect fit for them.
Yes.
Help them get more.
But somebody needs to reserve the meeting room, and that needs to be a member.
Yeah, and yeah. So okay, let's work towards that Maker Nexus and maybe try to get some physical meetings going later this year. While we're at it, presentations is everybody's job. Okay, Stephen with a PH. Williams is our program chair. But programs is everybody's job. So if you know of someone, in the business, robotics, or has an interesting story, don't book them. Just, ask if they're willing to do a presentation, and then get with Stephen Williams, and he makes the call. Presentations is everybody's job. So we always have world-class presentations. So I don't want to let up on that. Including this evening, our own Mr. Mike is going to be doing the presentation. So,
Oh, sure, set me up to fail.
well, our story. And March is our 20th anniversary HBRC presentation, or HBRC challenge, I should say, where you are doing the presentation. Everybody should be building robots, and this is a good deadline to show us what you're working on. So March will be our 20th HBRC challenge, and I'll post a link in the chat here with our challenges. We've got, of course, the table bot challenge, the floor bot challenge, the orange bot, the arm bot challenge, Let me share my screen again. Table bot challenge, floor bot challenge, amazing line bot challenge, which we kind of need to be there for that. But if you got a line following a robot, you can show it off through Zoom. My favorite, run what you brung. We're the homebrewed robotics club, so build your own robot and bring it and show it off. Also, Robo Magellan trials. I'm working on a Robo Magellan robot that's in my living room right now. It's made with a Huffy Green machine. But anyways, moving right along. What else? Any more club news out there? All right, let's move on into show and tell. Who's got a robot they want to show?
Hey, Camp, before you get into that, there was
Hello,
one,
Jim.
there was
Jim
one
Denizio,
news,
ladies and gentlemen.
hello. There was one news article I forgot to mention here, or just saw that Elon Musk's humanoid robot, the Optimus, he's making
Optimist.
Optimist, yeah. He's saying it's the most important thing Tesla is going to be doing and could eventually exceed the automobile division.
I caught that, but I withheld mentioning it. Isn't that a dude in a rubber suit?
Yeah.
Well, that having been said, the real key to Tesla is not the electric car, but I think all the data he's collecting for self-driving. So, I think at the end, Tesla and the self-driving technology that he's developing that he plans to use with his humanoid robots and his 21st century factories and so on and so forth. So here's to Elon Musk. All right.
Yeah. Hope he succeeds with his
Yeah, well, they're doing full on humanoid from what I could discern. So that'll be interesting.
They're putting money in. That's where that's what really matters. Money where their
Exactly.
mouth is.
Exactly. All
Camp, I'll just remind you that normally you ask for people if they need any help before you do the robot show and tell.
All right. What I need help with. Thank you, Wayne. Folks working on stuff need help with something. Now's the time to ask your question.
Well, I do. So even though I'm talking about behavior trees, my sample code uses the Nav2 stack to move the robot, but it's using it with a lot of code that I wrote to talk to the Nav2 stack. And there's supposed to be a, 6 lines here you are way to talk to the Nav2 stack. And I have yet to discover how to do that. I can talk to it in 6 lines, but when I tell it to move the robot, nothing actually happens. And when I look at the underlying code in the Nav2 stack, it's it's empty bodies of code. So I still have a lot more code to read, but if anyone knows the magic, let me know.
Mike, you started that out with 6-line intro to Nav2. What did you call it?
A 6-line interface to the Nav2 stack. You're not supposed to have to write a lot of code. And for my robot to ask the Nav2 stack to move the robot around the house, it was like, I don't know, 30 lines of code, 40 lines of code. We might actually look at the end of the talk. But I'm having to actually call an action handler in the Nav2 stack and request an action and track its completion and things like that. The Nav2 stack is supposed to do all that for me without having to get down to that low level.
Well, I think in the navigation too, you have to give it the boot up navigation behavior tree. Otherwise, I would look at the interface for the action servers, right? Because those are messages. And then
Yeah.
if that's the route, I would think that you want to be able to send a message to an action server like navigate to pose or something.
Yeah, I am using the action interface. But yeah, so, it's ROS2, so there's a bunch of different workspaces involved, and one of them brings up the Nav2 stack, and it gives it all that stuff about what behavior trees to use, what plugin modules. But now that I think about it, my code does not. Mine's in a different module, different workspace. Maybe that's the missing part. Thanks.
And there's always Commander, which is their API Python. That's supposed to help out. It's a higher level above the behavior trees.
I'm not aware of that. Could you post a link if you get a chance?
Sure.
Any more what I need help with? Thank you, Chaz.
Welcome.
All right. Well, I have a quick show and tell here. So I put my ultrasonics and my camera on the Nito bot back with the TurtleBot superstructure. It's too much weight there. Let me share my screen. That's why I'm moving into a 5-inch wheel diameter. Incidentally, we're having some fun with the example robot. So this is the bot back running the bot back package. And I've got the camera on board. And then this is ultrasonics here. We put this together at the ROS discussion group using a plain HCSR04 ultrasonic Python package on Raspberry Pi and melded that with the simple publisher tutorial from ROS2 and displaced the hello world string message with a range message, which incorporates all the things therein: minimal distance, maximum distance, field of view, and the actual distance measurement. So what you see here is an actual ultrasonic reading in a ROS2 topic. And so I'll drive the robot forward here with teleop, and you'll see the ultrasonics getting smaller and smaller. Here you can see it's at like 40 centimeters. I'll drive a little closer, and now I'll go backwards. And so, just trying to come together on this smart table. Now, Mr. Mike showed me a neat trick yesterday, and that's this ROS2 topic echo click point. I used to select a position in RViz and then have to go back to the terminal screen to capture the location. But here with the click point, okay, I'll go back to my map now. And if I publish point, I can point press, I can click here, and it'll tell me where that point is on the map. There's your XY coordinate. And of course, the Z is the pose. So that's the XY coordinate in the map. Let me move around here a bit. I'm going to go all the way up here and publish the point, click. And there you see the XY coordinate for that. It's 6 meters, 2 meters, XY away from where I started my mapping. Again, if I do the pose estimate, no, not pose estimate, publish point here, that's really close to where I started mapping, within a meter, right? And so I'll go out here, into the living room, click, and you can see that that's XY coordinate 5 and -2 meters. And again, the Z is the pose of the robot, or the angular velocity. So that's what I've learned recently. Any more show and tell out there?
Sure. This is Ross with two S's.
Hello, Ross.
Hi, everybody. Well, I'm proudly holding up my Oak D light, which arrived a couple of weeks ago. And I'm having more or less good success. I even got it. I've now just last night got it to work on ROS. Installing it into the Ubuntu Ubuntu stack on my desktop, and just quite impressed by actually what it can do. And there's certainly a number of folks.
Was there anything particularly difficult about getting the ROS package to run on it? Ross?
No, not really. There's a fair amount of compiling that goes on, but yeah, you just follow the scripts in the GitHub, github.python, GitHub depthai.-ROS, and carefully follow what's written there, and it works.
Very good.
The demo generates the stereo disparity image and an RGB. It shows in the RQT image view just fine.
Okay.
You can select the different
Did you
topics.
try to get it through RViz?
Yes, and I guess it got late at night when I was doing that, so I got the image to show, but not the disparity image did not show on the out on the floor, as it were.
So you can get.
Ross, can you just repeat the name of that device?
This is
If you don't
an Luxonis is the company. Luxonis, Luxonos, Oak D Light.
Got it.
And this
Thank
is
you.
the thing that went on Kickstarter about 6 months ago, and me and several thousand other people made their bids. And I was one of the lucky, I guess, one of several thousand lucky folks that made it in under the special introductory offer, I guess, as it were. And it took about a month after it was confirmed shipment to arrive here up in Toronto via Hong Kong, and it basically works. The big problem I've run into, and I just abandoned it. I have a Mac M1, which has an ARM64, as probably most folks know, and the Python wheels aren't ready for it, so it didn't work. But so I cannot run it native on my Mac, but the Ubuntu works just fine. I installed it on a Raspberry Pi 4, where the install took about 35 minutes to run, whereas on the Mac it took about 2 minutes. That's not a fair fight. So
you're actually getting video through RViz too?
correct.
Getting video through
I have a
RViz.
suggestion.
Yes, Mike?
Oh, so two things. One, I'm using an M1 Pro Max Pro.
Oh,
For
good. I
everything
want to
I'm doing.
communicate with you then.
What I do is I run Linux on a virtual machine using Parallels.
So do I. That's exactly that's what I do use. Yeah.
Oh, okay, so
My reference to
so far,
Ubuntu is
everything-
actually a parallel. It's the Parallels virtual, correct?
yeah, I'm using the Parallels version of Ubuntu. I've tried the other direct versions and so forth. So, communicate with me. We can talk about that. Although I have very few problems with it, other than
Yeah,
the Z.
I've got a couple of GitHubs where they talk about developing a point cloud and doing Slam with it, which is what my intention is to do.
Right.
I'm,
The other thing is,
I'm actually going to
that,
put
you
it on.
said-
I'm going to put it on this, which is my
oh, excellent.
which is my Nanosaur. And,
So-
and the
Right.
developer of the Nanosaur got his OAK a week or so ago, and we're already communicating about what to do. He's going to put it
You're
into,
getting the RGB video and the depth. Did I hear that right through RViz too?
no, I didn't get the depth to work yet.
You're getting
So
video.
my
through
other
RViz too, though.
suggestion,
Mike, go ahead.
yeah, so my other suggestion, Ross, is if you have a topic like, slash depth, something or other, if you go and do ROS topic echo on it, then just go look at the very beginning of what gets echoed. You'll see there's a header with a frame ID.
Okay.
Go into RViz and change your global frame to that frame ID. So if your frame isn't tied into the whole TF tree and you're looking at some other part of the TF tree as your main frame, RViz will not display anything that isn't hooked off from the frame that you've hooked into RViz.
Yeah.
So just set it to that frame, you'll probably see your depth map.
I'm following you because when I went up to pick the frame, there was a whole list of things I could have picked, and I ran out of time and more frustration as to getting the right combination of which one to pick and which topic to pick, and I went to bed. So
Yeah, just use topic echo to see what the frame is that's being
but
published.
anyway, I'm just going back about 10 years when I was getting my Connect working on the original Turtlebot, and this was easier. Of course, I guess I'm 10 years smarter than I was then, but maybe. Anyway,
You're not getting older, you're getting better, Ross. Hey, in the documentation there, you've got the RGB, but is there an indication that you could actually get the AI stuff into ROS through that?
I have no idea.
Okay.
I suspect there is.
Yeah.
In fact, you know what? Give me a week. The
You're getting it through-
the
You're getting it
Nanosaur
through the
developer.
Depth AI. You're getting it through the Depth AI demo, right?
Yeah, right. But not through ROS. But hold on, the developer is actually he works for. His name's he's Italian. Raffaello Bongi works for Nvidia, and he's giving a talk next week on Isaac ROS and how it can be applied to the Nanosaur. So
Excellent.
I think that will be a huge enlightenment. And he's actually posted a repository for the Nanosaur just yesterday. So I haven't had a chance to actually look at it, using Isaac ROS, and has built and makes available the Docker container to run all that. Anyway.
Actually, I do have some extra news. Xilinx actually, and this is old news, but I did not know they started a hardware acceleration group inside of ROS2.
Oh.
And they're providing a kernel ready ROS2 with firmware with their ARM FPGA front dev board, the K26. And so I think that's quite interesting because Nvidia is obviously providing those same similar acceleration package on perception, and I guess at one point they should be getting together. And I'm hearing that Nvidia is hiring around Isaac ROS. Now that you mention it, ROS.
Yeah.
With 2 S.
Good. Anyway, it's nice to be able to show it off to this group. Look forward to interacting with any other folks who are finding interesting things for it to work.
All right. Thank you very much. Ross with 2 S's from Canada. Formerly in Silicon Valley.
Formerly Foster City. right?
Yeah, yeah, good times. Say, Big Jim D, you have Big Orange show and tell?
Yes.
Wow.
So I've, remember Scott Horton? I don't know if he's here today, but he produced some really. He was in the contest for the Oak with using the Oak D and produced some great code and a tracking, particularly in this case a following. He demoed a robot following him around the house. So I wanted to get this implemented in Orange, and so luckily, his code uses this. We both use the Oak D camera, and the code is for that, and so I could actually really speed up by looking at his code and cribbing from it. So right now I've got to the point where I've got the tracking myself working first, not the whole following thing. So this is a step in the process. So right now, if you can see, the camera is moving back and forth here, tracking me, and then you can see in the screen share what it's seeing. And I've even got it to move the whole robot. If you go far enough, it will actually moves the whole robot, and I'm still working on it's kind of a difficult thing with this robot to get it to just move a little bit and not too much or too quickly. But the idea is that like you turn your neck, a human turns their neck and then eventually their torso to turn to the object that they're trying to track. And so that's why, you want to move the robot itself as well. And so now I've got it. So this is a step in the process. I'm almost coded up the following, and I'm going to be trying that out over the next few days. But it has all the information there. One of the interesting things here as well is I'm switching the model when it goes into tracking mode. It uses a mobile net model, which has a person. One of the objects is a person. It's only got like a dozen or so or less, but it also has a tracking. The model or several of the models that work on the Oak D have object tracking as well built in. And so what that means is it'll assign an ID to an object. Like right now, mine's already at 26 because I've probably gone off. But if I go off and then come back on, it usually will, it can attempt to get back to the same number if it's quick enough. So the idea is that you could, it'll say tracked or lost. And then if I come back, see, it still says number 32, or well, it went to 33, but when it's working well, it'll keep the same number. So you can tell whether the same person is being tracked when it's working properly. So that's in the model. But the X, Y, and Z, the depth is there, so I can tell the robot to go up to the person and set the goal using the whole LiDAR.
I need to recharge my battery.
Oh,
I am going to the recharge station.
oh, it looks
I'm
like
going to the recharge station.
looks like my robot is giving up and going back to recharge.
Got a mind of its own.
Well, you've seen this part before, I think, where it goes back to the charge station. But anyway, I wasn't planning to show that again. Anyway, I'll stop here unless you want to see this.
Yes, we want to see it. So it's autonomously making its way back to its charge station?
Oh yeah, can you still see it in the camera? All right.
Yes, that's awesome.
Yeah, this, I think I showed a video of it before. This is a live demo, folks, live. Anything can happen. Oh, there it goes. Now you can see the screen, it's charging. I changed the firmware on the STM32, on this, which is the board that comes with the SlamTech. It's the microcontroller board system. And that's what you see in this. If you can see the serial output here, it tells you the battery voltage. And then now that it's charging, it says charging, and the numbers will go up. It's basically just based on volts. So it's interesting. This battery goes, it's a 12-volt battery, but it will go down to like 8 volts, 8.5 volts, and the whole system will still run, the PC and the motors, everything. But if you go much below 17%, like below 8 volts, it'll shut down the PC. Anyway, it's interesting power issues. That's it.
Big Orange, I'm a fan. Let me
Thank
find the applause here. Yes, I'm applauding. Very nice, Jim. Thank you very much. Any more show and tell out there? Come on, I know we got one more. All
Looks like
right.
we have one hand raised there, D. Davis.
Oh, no, I was just applauding.
Hey, Dee Dee, how you doing?
All right, and yeah.
Good to see you. All right. Okay, then, moving right along. Let's get to the main show here, our HBRC presentation by Mr. Mike. This is Behavior Trees for ROS by Mike Wimble, Renaissance Man. Mike Wimble, formerly senior software engineer at Microsoft and ServiceNow. He's currently CEO at Retired, working on robotics and new inventions and developing personal assistive robots. So without any further ado, our own Mr. Mike Wimble, thank you very much.
Here I am talking and nobody's listening. All right. All right. So this talk is a series of slides. Let's see. Are you seeing this thing that says behavior tree for ROS?
Yes.
Okay. Since I'm not looking at the chat or anything, each slide has a little bit of audio. I'll stop at the end of each slide if you got questions or something like that. Just speak up. Okay, this first part hopefully will tell you everything you needed to know about behavior trees. Then there's up to 3 other parts if we have time.
Why should I care about behavior trees? Well, because they save you a buttload of work and make it relatively easy for you to get your robot to move with purpose. Once you write code for your robot that goes beyond the simple tablebot sort of task, it gets hard. State machines and such explode with complexity, are hard to understand, and are very hard to evolve. Behavior trees offer a human-readable way to generate complex behavior that can be evolved. You can add safety checks like test the battery charge and motor temperatures. You can create a behavior that, say, sends your robot back to the charging station, then picks up where it left off, and use that behavior over and over throughout the tree. Your code can be highly reactive, changing its behavior quickly as the situation changes. You can visualize and debug a behavior tree. And 6 months from now, when you come back to your behavior tree, you have a good chance of being able to understand what it did and pick up where you left off. There are several software packages out there that implement behavior trees. I'm only going to talk about one of them, behaviortree.cpp, and how you can use it with the robot operating system, or ROS. There are lots of aspects of behavior trees I could talk about, such as mathematical proofs, how they compare to other design techniques like finite state machines and utility trees, but I'm not going to talk about any of that. I'm going to try to tell you in a short period of time how behavior trees work and how to get them to work with your robot. I'm going to have to skim over a lot of detail to keep this short, but there are links at the end where you can learn more. This talk should help you to get up to speed quickly when you look at the linked videos and papers. With behaviortree.cpp and with the other interesting open source package Groot, you can quickly get your robot doing fairly complex behavior after writing a small amount of code.
Audio all good on that?
Yes.
Here we go.
Behavior trees are, well, trees. They have a root node, and nodes can have subnodes. Nodes are the boxes in the diagram, and the lines below a node connect a node with its child nodes, while the line above a node connects it to its single parent. Only the root node has no parent. Leaf nodes in the tree, that is nodes without any children, are usually either condition nodes or action nodes, and often connect to a little bit of code that you write. Condition nodes often test some state on your robot, like whether the batteries have enough charge or whether the robot can see the refrigerator. Action nodes do something like move the robot around. In the literature, nodes that have children are called control flow nodes as they guide the execution of the behavior tree. Behaviortree.cpp provides a handful of built-in node kinds, and we'll talk about some of them. You will extend that set by adding your own condition and action nodes. You can even add your own kind of control flow nodes, although that's less common. The picture is showing a silly example behavior tree as visualized by the group program. Behavior trees are written as XML files, and you can use any old text editor to create one, or you can use Groot graphically to create a tree and save it as an XML file. Groot will also allow you to visualize the real-time execution of the behavior tree on your robot. The picture shows some of the features of a node as it's displayed in Groot. This is a custom node I created, not one of the built-in node kinds. The A : says that it's an action node. The turn in relative direction is the name of the node I just made up. Names should be descriptive, but they also correspond to some code class that implements the behavior. When you create a custom node, you will also create some code to match. The turn the robot, keep track of where it's been is just a description I provided. Helps make the node humanly readable, especially to others. So be concise, but complete in what you say. Nodes can take parameters like function parameters. A parameter can be an input to your node, output from your node, or both input and output. The make opposite turn parameter is an input to the node, and it will be given the value of false when the node is executed. This is just a string value. The previous pose is an output value from the node, and total path is both input and output to the node. A behavior tree includes a blackboard, which is just a key value data store. Any node can read from the blackboard or write to it. For instance, you may have a node that looks for wall outlets and adds to the list of known wall outlets. It reads the old list from the blackboard using the key name known outlets and adds any new outlet locations it discovers to the list and writes it back to the blackboard. Somewhere else in your tree, another node can look at that list and select the nearest one to the robot and send the robot off to plug itself in and recharge. The parameter values for the node can either be constants from the XML file or can be in the blackboard, possibly using parameter remapping, which is what the total path parameter is showing. Rather than read and write the blackboard value with the key name of total path, the key value name of path taken so far is used. This helps avoid name collisions where several node kinds want to use the same parameter names for different purposes. Each kind of node acts differently, but they have some things in common. Every node has a state value. Nodes that aren't yet being executed are in the idle state. Once a node begins executing, it enters the running state. From there, what happens depends on the node kind. A retry until successful node will execute its one child node over and over until the child's node state becomes success or until num attempts have been made. If the child node becomes successful, the retry until successful node becomes successful as well. And in the picture, that state will be passed up to the root node. If num attempts to execute the explore all cells reactive fallback child node were made, and each time the child state was failure, then the retry until successful state also becomes failure. The process of executing nodes is called ticking a node, and it's done by actually calling a tick function in the code corresponding to the node. A node that is tick immediately gets its state set to running, and the node itself can later set its state to stay in running or change to success or failure. While the node state is running, it's still active and passes that running state up to its parent, and it passes up to its parent, and so on. Once a node state becomes success or failure, though, the parent's node kind comes into play. For instance, a reactive fallback node, like the explore all cells node in the picture, acts like an OR operator. It attempts to successfully complete its goal by ticking its children left to right until one of them succeeds. If none succeed, the reactive fallback node status is set to failure. In the picture, the reactive fallback node is in the running state, so it begins by ticking its first child node, which tests to see if all cells have been explored, whatever that means. The test failed in this example, so the have explored all cells condition node state gets set to failure. The reactive fallback then goes on to tick the next child node, the reactive sequence node, which will then enter the running state itself. The two most important node kinds in a behavior tree are the reactive sequence and reactive fallback kinds. While the reactive fallback node acts like an OR operator, the reactive sequence node acts like an AND operator. It succeeds only if all of the child nodes succeed. If any child node fails, the reactive sequence fails. Looking back at the previous silly tree, the tree reads, if I have sufficient battery charge and my motor temperatures are fine and my life insurance is up to date, then watch me do something stupid. If all of those child nodes enter the success state, the hold my beer is a success. If any of them fail, then hold my beer is an epic failure. A quick note, the literature mostly talks about sequence and fallback node kinds. In behaviortree.cpp, there are two kinds of sequence and fallback nodes, a pair that have memory and a pair that don't. I'll explain that in a bit. I just wanted you to be prepared for the other terminology when you look at the linked material later. Let's jump right in to design a behavior tree, which I hope will make things even clearer. Along the way, we'll learn about some of the more important design patterns that will help you to get it right early on. The problem to be solved, or goal, is to have my robot patrol my house once. I will divide the floor plan of my house into a rectangle of square cells. If a robot moves into a cell, I consider that cell explored. When all the available cells are explored, my goal is met. But not all cells can be explored. Some cells might contain an obstacle. Some might contain a danger, like a stairwell or swinging pendulum full of flaming spikes. My robot must avoid these cells, but it must otherwise move to all other cells at least once for the goal to be met. The first design pattern is that you create as your first node below the root node something that encapsulates the end goal. So we create a node whose goal is have explored the whole house. It doesn't matter at this point what kind of node that is for this discussion, though technically you should start out with a condition node. This node probably fails at the start as the robot is sitting somewhere in the house and has only explored that one square, so we move on. I'm making that first node a retry until successful node because the strategy I want to employ is to repeatedly try to do one of two things in order to explore all of those cells. The node kind that selects among a set of strategies, as we discuss, is the reactive fallback node, so it's the next child node we create. The retry until successful node should place a reasonable bound on how many chances I'll give the robot to find a path to patrol the house. I probably don't want it to spend a year to patrol the house just once, maybe not even a day. Pick some number as a reasonable upper bound on the number of attempts to use the two plans I'm about to explain, and put that number in the num attempts field. So here's how the robot's going to explore everywhere. When a robot is on any cell, it looks at its 8 neighboring cells. If there is at least one cell that hasn't been explored yet, the robot will randomly pick one of these cells and move to it. This just keeps going on until the robot finds itself in a situation where it has already explored all the neighboring cells. That's not necessarily a success, though. Imagine that a robot was placed in front of a closet to start. It moves into the closet and is surrounded by walls, and the only way to move is to back out to the cell it came from. Whenever the robot doesn't have an unexplored neighboring cell, it backs up to the cell it just came from. Then it repeats the algorithm: explore an unexplored cell or back up to the previous cell. Eventually, one of two things will happen. The robot will explore a cell, and all the available cells in the house have been explored, and the goal is successful. Otherwise, the robot is backed all the way up to the starting cell, and there are still cells it hasn't explored. That means there are pockets of cells in the house that the robot can't get to, like a room with the door closed. In that case, the goal failed. Failure is always an option.
So if that wasn't all clear, a little later in the lecture, we're going to actually take this behavior tree we're creating and run it under a paper simulation. And you'll see better what I'm talking about with these neighboring cells and such.
Say, Mike,
Yeah.
is your tree aware of the global map, or are you just looking at local cells?
The code that I would write to implement this tree. So remember, I said there are condition nodes and action nodes that you probably have to write. You'll put them in the tree, but behavior tree.cpp doesn't know anything about your robot. So you need to write a little code that handles conditions and handles actions. So the code that I would write to implement this doesn't really know much about anything. It just the thing that says, are there any neighboring cells, looks at the LiDAR and says, I'm going to arbitrarily pick, say, a 1 meter square as my cell size. So I'll use the LiDAR's 360-degree scan. And for each of my neighboring cells, I'll ask the LiDAR, is there something in that cell? If there's something in it, then it's forbidden. It's a blocked cell. I don't have to worry about it. But if there's nothing in it, then the only other thing I need to know is, have I been on that cell before? So I will have a little data structure, an array in my code, that every time I enter a cell, I'll set the Boolean that says, yep, I've been to this cell before. So the condition that says, what you're about to see, is there an available neighboring cell? Will just look at that array and says, for my 8 neighbors, whatever square I'm on, look at my 8 neighbors. And if any of them have not been visited before, then there's a place I can go. If all of them have been stepped on by the robot, then I can't go to any place directly. So I'll back up to wherever I came from before I got here.
Same question, though. Does it have any awareness of the global map, or are you just looking at local cells and what you can do?
Just looking at local cells and what I can do. The only thing it knows globally is, for the whole house, is there at least one unexplored square left? So it does have to have a sense for how big could the house be, and how many squares haven't I seen? So you start out, if the house is 30 by 40, you build an array of 30 by 40 cells and you put them all as unexplored. So in that sense, it has some global sense about what that.
Okay. And flaming pendulum, excuse me?
Well, yeah, if anybody understands that, that would be you. Flaming pendulums with,
it's a trap.
Pendulums with flaming. So again, I'm not looking at the chat while I'm doing this. So if anybody has any questions, just speak up.
The next design pattern is called the PPA pattern for postcondition, precondition, action. it says that you should expand the fallback node with a child that tests for the post condition already being true. That is what the fallback node is trying to achieve. Then the other children are sequence nodes with alternative strategies to achieve the post condition. And each of those sequence nodes gets expanded with left child precondition nodes and right child nodes to achieve the strategy. Now that's a mouthful. Here's what it looks like. So expand the fallback by adding a node that tests for the post condition. That is, check to see if all cells have been explored. If that condition is already success, then the fallback is success and we're done. If that condition is fail, though, then we have a list of strategies to try to achieve that condition. In our case, the robot tries to explore a neighboring cell if there is an unexplored neighbor, or the robot backs up to where it came from before it entered the current cell, if that's possible. If there are no neighbors to explore and the robot can't back up anymore, we're done and the robot failed to explore all cells. The second part of the PPA expansion said that the sequence nodes should have left child nodes that test for any preconditions and right child nodes that achieve the strategy. For the sequence explore a neighbor cell if unexplored, the precondition is that there must be a neighbor cell that is unexplored. If the robot is in something like that closet scenario, there won't be any unexplored neighbors and the sequence node fails. If the precondition is true, though, the next child node picks a random unexplored cell and moves the robot there. The last node in the sequence may not be obvious to you at first. Remember that the parent explore all cells fallback node will succeed if any of the child nodes succeed. Well, if we move to an unexplored neighboring cell, and that was the last unexplored cell in the house, then we're done. The fallback node found a strategy that succeeded without having to look further. So we make the sequence node succeed if, after having moved to a cell, the post condition succeeds.
Hopefully this will be, if it's a little confusing, hopefully it'll be less confusing once we get to the simulation.
If the explore a neighbor cell if unexplored sequence node fails, one of two things must have happened. Either there weren't any unexplored cells, or the robot moved to an unexplored cell, but there are still outstanding unexplored cells. We don't want to execute the backup strategy until there isn't any way forward from the current cell. Otherwise, the robot would be in a situation, say, it comes out of a closet and then backs up again into that closet. Now all the neighbors have been explored or are forbidden. So the only thing the robot can do is back up again, thus leaving the closet a second time, and then it would back up again right into the closet. This is called chattering behavior, where the robot makes a sequence of moves over and over without making any real progress. In expanding the backup to the previous cell sequence, like before, the sequence expansion begins with a precondition test. We don't want to back up unless all the neighboring cells have already been explored or are forbidden. We want to always move forward to a new cell where possible and only back up otherwise. We already have a condition node that tells us if there are any neighboring cells unexplored. We just need to invert that. We don't want to create another custom condition node for all neighbor cells are explored, as that would just make more code for us to have to write. If there aren't any free neighbors, the robot backs up and, just like in the previous sequence expansion, we finish off the sequence with a test for the post condition for efficiency's sake.
All right. This is the complete tree that we're going to play around with later on, but there are some more design patterns I want to tell you about.
Remember that I said behavior tree.cpp includes memory and non-memory versions of the fallback and sequence nodes. So far, I've been showing you the non-memory flavor. In behavior tree.cpp, the reactive fallback node is called reactive fallback, and the memory fallback node is called simply fallback. It's the same for the two kinds of sequence nodes. A memory node includes a memory of what has been done so far and avoids redoing that work. For example, When a memory fallback node enters the running state and begins ticking the child nodes, it remembers which children have already responded with failure, and it doesn't tick them again when the fallback node is ticked in the future, at least until the fallback node finally succeeds or fails. Then it starts all over again with the first child. It works the same for a memory sequence node. Once a sequence starts ticking its child nodes, when one of those children enters the running state, that gets propagated up to the sequence node and propagated up to the parent and so forth. Eventually, that sequence node will get ticked again, and rather than ticking the first child again, a memory sequence picks up by ticking the child node that last reported running. So it doesn't re-tick the left child nodes until the sequence itself finally succeeds or fails. Then it will begin with the first child all over when it's next ticked. Memory nodes are non-reactive. By that I mean that if something has changed that would have affected the left child of a memory node, the memory node won't know about it and not react to it until the memory node finally succeeds or fails. For instance, if a memory node sequence has a precondition node that the motors aren't on fire and goes on to tick the move somewhere child node, then if the motor suddenly bursts into flames, the sequence node will just keep on trying to move the robot, all the while spreading flames and ruin throughout your house. It's the same for a memory fallback node. If it has a child node that tries to go through a window and can't because the window is closed, the fallback node goes on to the next strategy of up on the housetop, click, 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 which involves the long task of finding some flying reindeer, feeding them, harnessing them to a sleigh, getting air clearance, and so on. Meanwhile, if Mrs. Claus opened the window during all of that, the memory fallback can't react to it and change its strategy. Memory nodes commit your robot to a behavior and are non-reactive until that strategy completes. The safety design pattern is that the left children of a sequence node should guarantee the safety of the robot. A sequence is an and node, or think of it as an and then node. Do safety and then do the other stuff. The right nodes of the sequence should be reactive, as just mentioned, so that if the safety constraints suddenly signal failure, the reactive right children can be abandoned until safety is achieved again. The have sufficient battery charge here might not be a simple condition. It might be a subtree behavior, which I'll describe in a bit, that saves the current pose of the robot, goes to the nearest charging station to recharge, and then returns to where it was and continues on.
Say, Mike, question?
Yeah.
So in the behavior tree, you're using actual RVIS2 XY cells?
Yes.
So
But so if you mean the locations, like the X and Y locations, then
yes,
yes.
when you create the
But
map,
right, I'm going to say that the home cell goes from X00 or XY00 to XY11. Okay, that's one cell. So if the LiDAR or the SLAM or anything says I'm anywhere in those coordinates, then I'm in that home cell.
so these correlate with the map that you created with SLAM Toolbox.
Exactly.
Okay, but when Miss Claus opens the window and the robot goes out the window, this is unknown territory.
No, you have a map of the house or a map of the yard, and in the yard there's a house with a door and a window.
So in this case, that got mapped.
It'd be part of your map, yes. In this that's exploring my house, I start out with no map at all. I just need to know what are the boundaries of the house. And this thing, as it goes along, just like when you run your robot through the house to build a map, this will do that same thing. It starts out knowing nothing, and it just says, go to some place I haven't been, extend the map that I've got.
Oh, that's awesome.
Hey, Mike, I have a
You don't
question.
have to, just one sec. So you don't have to have a static array for your house. You could just say that my house is 1 meter by 1 meter. And then you say, oh, wait, I see more space. Let me expand that map. Let me expand my array to include the new area that I know about. Okay.
So this will be mapping even as you're exploring.
It's exactly what it's intended to do. Create a map of the house by looking at everything. The other question?
Yeah, I have a question. So in this example you have on the slide, you have the safety checks before it actually does the action that you want it to do. Do I have to put these safety checks everywhere, or is there some way to put them in a place where, like, if any of these become true, then go into a different state or do a different action? You know what I'm saying?
So, yes. So if you've done this correctly, that you kept your nodes all reactive and you don't have memory nodes in them, then, and I don't say that that's correctly. There are times you'll want to use a memory node and you'll discover the few times you do. But if they're all reactive, then you could have way up in the top left of your behavior tree something that says I have sufficient charge. Okay, and then you're way down into the middle or the right of your behavior tree doing something over there. Well, if that condition changes in the upper left to where it's false, and this may not be clear to you because I may not have explained something clearly here, that every node, when it runs, is expected to run almost instantly. If you are doing something that takes more than an instantaneous piece of time, you set your node to running, your state to running, and running gets propagated up the tree. And the way the behavior tree works, which I haven't told you yet, is you have about 6 lines of code in your main program. And that 6 lines of code says, create the behavior tree using the XML file. And then as long, I'm going to tick the root node. As long as that root node says it's running, just tick it again. Tick, 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 tick. And so states that are doing something like moving the robot, they don't move all at once. They move an inch and they set their state to running. And so this thing goes all the way back top to the top. It starts working its way back down. And now you've got this node that says, oh, I'm out of battery charge. Well, it'll do that. And then, you know, this thing should be, how do I want to say, it should be reacting to the overall state of the world. So once the battery's charged, you should find that everything that you had done before, well, it should remember, because of the state of the robot, that it doesn't have to do those things again. And it'll get right back to where it was and try to pick up where it left off. So you do not need to put these safety conditions everywhere unless you've designed a tree that isn't reactive at some part in it. And if you've done that, you want to repeat safety conditions where you need them.
I think that the key understanding there is the tick. It's like a heartbeat, right? And it's going through the tree with every tick. It sounds like.
Understanding that a tick is supposed to execute quickly. And if you can't execute quickly, like the navigate to pose sort of behavior tree node, it's going to take, seconds or minutes to get somewhere. So what it does is it says, I will start the robot moving, 3 feet away, but I'm just going to return running. And when you get back to me later on and you tick me again, I'm going to ask the Nav2 stack, have you finished moving to where I told you? No, I'm just running again. And I'm just going to keep polling the Nav2 stack until it says I either succeeded or failed to get to the point.
Right.
And then I'll set my state to running or success.
Right. Okay, that makes sense.
Good question.
Another design pattern is one that helps prevent chattering or moving between 2 nodes without making much progress. The hysteresis design pattern is that if you have a precondition test that passes, then don't go and immediately violate that precondition. Think about the battery charge test in this slide. If the battery has less than 20% charge and the robot goes to recharge itself, don't just charge it to 21%. Charge it to like 80%, so the robot won't soon need a recharge as it executes the right child nodes guarded by that precondition. Making your robot reactive is key to achieving safety and being responsive to the world that is changing around your robot. The precondition efficiency pattern is that if you have independent preconditions, ones which don't depend on each other, It helps to try ordering your precondition nodes so that the ones most likely to fail will come first. If you need to test for a good weather forecast, and that will take a few seconds and isn't likely to have changed much since the last time you checked, and you also need to check the battery charge, which is more likely to have changed since you last checked it, do the battery test first. It's the most likely to fail, and you can avoid working on that weather report and other children to the right until the precondition is finally taken care of. Another way to make the tree more efficient is using the fallback efficiency pattern. This says that if you have independent children of a fallback node, children that don't depend on the ordering of the other children, order them so that the most likely to succeed comes first. In the slide, if the robot is trying to get into a room, trying to go through the door is probably the thing that'll work most often. If the door is blocked, then maybe going through the window will work sometimes. But climbing up on the roof to slide down the chimney is probably a desperation move. If you're about to be nibbled on by tiny unicorns, you may need to keep all possible strategies in your book of tricks. But don't first try the ones that are less likely to succeed.
We're getting close to the end of this part.
Don't mistake a behavior tree as a piece of code. When you write code, there are design patterns that say, for instance, that a function should do one non-compound things, not, for instance, that the function does A and does B, and that the body of a function should contain only a few lines of code. While those patterns help make code readable and understandable, they don't directly apply to behavior trees. The reduced complexity pattern says that if you have a subtree of nodes that includes nodes that aren't likely to be used anywhere else, then don't expose the unnecessary detail in the behavior tree. Instead, create a node which wraps up all of that behavior. Fewer nodes in a tree makes it much more readable by humans. The code backing the node will handle all the fiddly details, but you don't need to show all that detail in the behavior tree. The common subtree design pattern also reduces complexity. If you have a common collection of nodes at 2 points in a tree, or even a collection of nodes that you think might be interesting behavior that could be used in some other behavior tree, then make a subtree out of it. A behavior tree XML file can contain lots of trees in it, and one tree can refer to another tree in the same file.
Okay, I'm about to start the next sequence, which is shorter. And let's stop this. If you have any quick things here, otherwise, what we're going to do is.
Whoops.
Go ahead.
Ask a quick question. So it sounds like it's pretty easy to get into an infinite recursion thing here. Is there? Am I missing something? Is there some reason why that doesn't happen?
This tree, every node can only have a single parent, so there isn't a graph.
Okay, and it's a fixed tree. It doesn't keep forking things underneath it.
There are extensions that people make to behavior trees. So there's a pattern called the utility tree pattern, for instance, where rather than having a fixed order of the children, what you do is you first ask all the children to compute a score as to how useful you think you will be. And then it goes and sorts the nodes dynamically and executes the most likely one. Similarly, there's a genetic programming sort of thing. It doesn't have to be genetic programming, but you can go and dynamically recreate the tree on the fly. Behaviortree.cpp doesn't really directly support that, but you could do that if you want. Just like there are ways of adding recurrent neural networks to a behavior tree. There are ways of using the behavior tree as a decision tree. There are ways of converting a finite state machine into a behavior tree. So those are possibilities.
Okay,
But if you introduce recursion, you will have held a pair.
Got it. Thanks.
The common subtree design pattern also, oops, wrong thing to share. Let's see, there we go. Uh-oh, that's, why is it? Keep wanting to show that, just a second. This is a guy I want here. And where's Zoom? I've lost my Zoom. Share. And animation. There we go. Let's see if this works. Let's create a simulation on paper of the robot executing our behavior tree that explores a house. The grid in the upper right will show the robot as it explores the house, and I'll annotate the tree on the left at interesting places along the way. At the start, the robot is placed in some arbitrary place in my house. 2 of the neighboring cells are forbidden to the robot, but the robot could next explore any of the remaining 6 cells. I've stopped the simulation here, and we can see that so far, the have explored all cells condition node has reported failure. So the explore all cells fallback went on to tick the next child. That explore a neighbor cell if unexplored is still in the running state and has ticked its first child, which has successfully reported that there is currently an unexplored neighboring cell. The sequence's next step then will be the tick to move to a random unexplored neighboring cell node. At this point in the simulation, the robot moved to a random neighboring cell, so the action node returns success, and the sequence went on to tick its third child, which checks to see if all the cells have now been explored after the last move. They haven't, so that condition is reporting failure. And the next thing that is going to happen is that the explore a neighbor cell if unexplored node is going to enter the failure state. That will be propagated up and will cause the explore all cells fallback node to go on and tick its third child, the backup to the previous cell node. The backup to the previous cell node will tick the inverter node, which will tick its child node, which returns success, indicating that there are unexplored neighboring cells. So the inverter will return failure and no backup will be attempted. The failure has propagated to the explore all cells fallback node, which in turn causes the retry until successful node to start all over. I'm going to just skip along for the next few movements, since as long as there is an unexplored neighboring cell, the robot just picks one and moves to it. So it's just the same behavior all over, and rather than show you the simulation, I'll just jump ahead to where something interesting happens. So I'm about to move down, and now when I move down, I have explored all the neighboring cells. And I'm not, as Kent pointed out when I was going over this talk, my robot doesn't allow diagonal moves in this. If you did add diagonal move allowing, it could jump to that cell to the right of the pink cell, but my robot doesn't. And so it's going to say there are no neighboring unexplored cells. Now the robot has no unexplored neighboring cells. If you follow the tree, you'll see that the backup to the previous cell is now in the running state, and it has ticked its first child, which says that all neighboring cells have been explored. So it's time to tick the next child, which will back up to the last cell. After backing up, the rightmost child of the backup to the previous cell sequence says that there are still unexplored cells. So the backup to the previous cell sequence fails. The explore all cells fallback fails, and retry until successful starts everything all over again. All neighboring cells have been explored here, so we back up again, just like before. And finally, we're at a point where an unexplored neighboring cell exists again, so the robot will move to it. I'll just keep skipping ahead until something new and interesting happens.
Now, something interesting is about to happen.
The robot finally moved to the last unexplored cell and marked it as explored. The postcondition of the explore all cells fallback node succeeds. So the fallback finally succeeds itself. The retry until successful node succeeds, and the whole tree succeeds. The behavior tree successfully caused the robot to patrol the whole house.
And I will copy these links and put them in the chat. Let's see, send it to everyone. And so these are, so now I've given you a gentle introduction. There are two other parts of this talk if we have time and you're still interested. The next part is I'm going to show you a demo of this thing actually running a simulated robot. It doesn't solve this problem. It begins to solve a different problem. But it's, real ROS2 code being driven by a behavior tree. It's a short movie. And then if you want, I'll begin to show you what is the actual code you have to write to get this to all work. So, and these links here, let me go and make that big again. So behaviortree.cpp, that's the, oh geez, let's try that again. So that's the package I'm talking about here. Groot is a package that you can point it at your XML file and it shows you those pictures like I've been showing you. You can also create your tree just by dragging things around in the graphical interface. And when you're all done, you can save it and it'll write an XML file for you. You can load it back in later on, unlike Gazebo, pick up where you left off again. So behavior trees and robots and AI. This is a pretty good paper. It's kind of at a college level on this thing. It's pretty understandable, but it does include mathematical proofs or some of the design patterns I talk about in here. Behavior tree and robotics. It's another paper. I don't remember the specifics on this one, but you're going to, before you really get your mind around behavior trees, you want to listen to this lecture a few times. You want to listen to this next thing, this Peter Ogren. He has a collection of videos on YouTube that are just really excellent about behavior trees. There's probably, I don't know, a dozen videos in the collection. I've watched each one of those 5 times or more, and then read the papers over and over. And so it just helps to get your mind fully wrapped around how to use these things. I have some code on GitHub that is the code I'm using to run the simulation I'm about to show you. You won't be able to directly run it without talking to me. And, it uses Ralph Knox Simubot that he talked about a couple of months ago as a nice gazebo RViz demonstration of a robot running in a gazebo house. And my robot is going to run under that simulation and then run a behavior tree to move the robot in that simulation. And then the last thing is, any discussion we have, you should be, going to our home website. You should be looking up the email list. You should be attending the Tuesday meetings on Zoom. And that's where any further discussion on here, unless you email me directly, is going to happen here.
Hey, Mike, can I ask a question?
Yes.
So can you quickly just go back to that point where you were looking, where the robot got to the very last cell? That was something bothering me about that.
Okay. Let's get back to Zoom. Zoom. Share screen. And this cell here.
Yeah, just right there. So now before it filled in the last R, let's suppose that somebody moved the table from row 2, column 3 to row 1, column 1. Well,
Ooh, boy,
I guess you could, the robot would bump into it if it got there, and then it would say, okay, there's something in the way. But how does it free up the cell that is now empty that it can go through?
So in the previous version of this talk, I told you how to actually write the code for this. What you do is whenever a robot moves to a new cell, it does 3 things. It first of all goes to this array and marks the cell as having been explored. The next thing it does is that there's a stack, and you push onto that stack the coordinates that the robot just moved to. So when you need to back up the robot, you just pop off things off that stack, and that's how you get back, do the backup move. So you mark the cell as explored, pop the coordinates you use to get to the current cell, or push the coordinates you use to get to the current cell onto the stack. The third thing you do is you rerun the neighbor scan. So at any time, an obstacle might show up in a square that you previously thought was unoccupied. Just mark it as occupied. That's fine. And the other thing that could happen is a cell that was previously thought to be occupied suddenly is not occupied. Aunt Maggie finally moved away from the bar, and now I can move in front of the bar. And in which case, just mark the cell as unexplored.
Okay,
And
so if I think I get it. So basically what you're saying is whenever you go to any cell, you would do a scan neighbors to see if anything has changed. Is that correct?
I would, yes.
Okay.
So I have, next is the demo. And back to Zoom, share screen. Do this. You see the black screen, right?
Yes.
Okay, here we go. This is a simulation of a robot on ROS 2. The simulation was made available by the generous contribution of Ralph Knock, and there'll be a slide at the end of my talk that will include a link to his code on GitHub. No, it won't. What you see here is the RViz 2 visualization of the simulation. There's also a gazebo visualization running in the background, but I'm not going to show that. Large red and green bars mark the 00 or home coordinates of the simulated world. Red points in the X direction, green points in the Y direction. There's a smaller set of red and green bars that show the position and orientation of the LiDAR on the robot. You'll see that more shortly when I move the robot around in the simulation. The scintillating red dots represent objects seen by the dashboard or the onboard LiDAR. Most of the dots represent walls seen by the robot, but the 4 dots just down and to the right of the home position are the reflection of the 4 legs of a table in the room. The LiDAR doesn't scan 360 degrees, it only scans 160 degrees. I'll spin the robot in place so you can see other features in the simulated house. You'll see a wall to the left of the robot appear as the walls to the right of the robot disappear from view. With a little more rotation, you'll see there is a hallway to the other rooms to the left of the robot
and that hallway has a doorway at the top. I'm going to demonstrate the beginning of a behavior tree that will be used to cause the robot to explore the house by following the walls of the house. The first part of the behavior is just to move the robot near the closest point of the closest wall. To do that, I've written some custom code for use by the behavior tree. Let me show you the visualization of that custom code. I have one ROS2 package that looks at the LiDAR points and tries to guess if they represent a possible wall. It shows its guesses in RViz as solid red bars. So you see if the code thinks it can see 4 possible walls or more. I have another ROS2 package that looks at those walls and computes the nearest point from the robot to each wall. They show up as the solid cyan bars. To make the demo a little more interesting, I'm going to move the robot so it's not at the home position, but rather nearer to the table. Because of the jitter in the LiDAR and the tuning parameters I chose for the wall discovery code, you may see changes in the wall's closest point bars. Now I'll start up my little bit of code that will use a behavior tree to move to about a half a meter away from the closest wall. This results in a thin green line showing up, which is a visualization of the path that the Nav2 Stack computes to go to the pose that the behavior tree computed. The robot moves along that path and stops about a half a meter away from the closest wall. I could move the robot to any place in the house and run the behavior tree, and it will move the robot to near the closest wall that the LiDAR can see.
All right. So the last part of this talk, if people want to get into it, is I will go over some of the code that you write and demonstrate that you don't have to write a lot of code to use behavior trees.
So Mike,
if you don't want to see,
you got 2 things going on here. One, where the robot's to go to every cell in the house, but 2, we're trying to find the nearest wall. Are those 2 goals coupled, where find the nearest wall, and that's the way it goes about traversing all the cells in the house?
these are completely unrelated behavior trees that I was developing. I was first writing a wall follower for the robot. And then I thought, well, the wall follower, it's got to deal with a lot of tricky situations. And that makes it ideal for the behavior tree. I'm getting an echo here.
But it could, it could be combined. Okay.
Yeah, particularly if you use a subtree pattern. So you could write a behavior tree that just does one thing, like wherever the robot is, go and recharge the robot. And you save that as a behavior tree. Now you write another behavior tree, and you might have a thing that says, well, if the battery isn't charged, go and invoke that other behavior tree. In this thing here, I could have something that says, place me next to a wall, and then go and do this, find unoccupied squares to go look of thing. There's not particularly interesting reason why you might need to go to the wall to start with, but you could. So the nice thing about behavior trees is this composability. Create behaviors that do them together.
Yeah, maybe it does the perimeter and then works all the internal cells or something like that.
Sure. And that's very easy to write in a behavior tree. And the code you need to write typically isn't all that much. So let's see if I still have code showing up over here. This does not look like my code. Just a second. Stop sharing. Screen sharing is paused. Stop sharing. Share screen. Why does it want to keep going back to that? Hang on, that operator error here. Quit that demo. Let's try this again. Sure, I don't suppose you see my code here, do you?
Yes.
Oh, yeah, just operator error here then. All right, so when you write your behavior tree, so here's the beginning of this simulated behavior tree. Ignore this, ignore this. So I've been experimenting with other stuff. And make all this stuff active. So here's the behavior tree that you just saw. There's a condition node that says, am I near a wall? And if and this is part of a fallback. So if I'm near a wall, I'm done. Otherwise, I have one strategy right now. There'll be several, but this is going to use a fallback to find a way to get near a wall. And the fallback is, one of the ways to get there is to move to the closest near wall. So when I was really designing them, I had strategies for what to do if the wall that the LiDAR sees is like within a couple of meters of the robot, what to do if the LiDAR sees a wall within 6 meters, and what to do if the LiDAR doesn't really see a good wall anywhere. And there were different strategies for how to explore the house. But this little bit, is the behavior tree for what we just saw here. The stuff down the bottom is just for Groot's sake. This tells Groot what kind of custom nodes that you're talking about and what are the input and output ports. That's not interesting except to Groot. So you write an XML file. It could be as simple as this. And then you need to write the code that, tackles that XML file and does something with it. And so here's what your code does. So there's a bunch of includes up the top. This is a typical main program. It starts out doing ROS-y things. It creates a node in ROS. And here it's doing some more ROS-y thing that says, go find from the launch file, what is the path to the XML file? And I'll use that path in a second. And then when the behavior tree reads in your XML file, it knows about these built-in nodes, but it doesn't know anything about your custom nodes. So what you have to do is tell the behavior tree package that if you ever see a move to pose node, then you need to use my move to pose class. If you ever see a can see close wall node in the behavior tree, then I have written some code that makes my class do that thing for you. So this is all just about telling the behavior tree about your custom code. So if you don't have much custom code, this is very short. Then you actually go and create the behavior tree. Oh, geez. Get back here. Using the Visual Studio Code, which is God's gift to programmers, but it can be a little reactive here. So this says take the path to the XML file and create the behavior tree. Start it in the tree variable. Now the next few things I'll have to do with visualization. One of the things Groot will do for you, besides just designing the tree and showing it to you nice in a pretty way, is when you run your robot, you can bring up Groot and say, my robot is about to go execute some behavior tree. Rather than reading an XML file, go interrogate the robot and show me the tree that the robot thinks it's executing, and show me all the states of all the nodes, show which ones are running and have failed and are success and all that, and it'll generate this little animation for you. And the way you do that is you hook your behavior tree through this ZMQ publisher thing. That's the one line that hooks it up to Groot. Now you have to go run Groot, but at least now Groot can introspect your robot. Then I also like to have on the command line a trace of how the behavior tree thinks it's operating. So this thing says right to the standard output, everything that the behavior tree thinks it's doing and why it's doing it. And then, since I want to make sure when I look at my terminal output that I know what tree it was running, I just say, print the tree out as an ASCII tree by recursively traversing the tree. So these things just set it up for logging so I can understand what's happening later on. Then the rest of it here, this thing, I go and, try to figure out what walls are close and all that. Well, I've written some code called closest point server, I think, or something like that, that goes and figures out what those closest lines are. And this thing subscribes to the topic and just makes it available for me to interrogate later on. And the other thing that I found useful is when I'm going to move the robot, I know where I want to move relative to the LiDAR. I want to move to this square relative to the LiDAR. But if I want to move the robot, I can't talk in terms of the LiDAR. I have to talk in terms of the maps frame of reference. So this thing says, just wait until enough of the system has come up so that the transform that I need is finally shown up. No sense executing the behavior tree. It'll just keep failing, doing nothing until that transform is finally available from all the other software that's running. And then here's the meat of your thing. It just says,
this on the web.
oh, shut up. This thing's, oh, wait a minute. This is part of the timeout here. Okay, then I just print a little status message saying the transform is finally available. I'm actually going to start. So here's the meat of this. It just says, I have this, well, let's just look at the while loop. So while ROS is still running, if I haven't hit Control-C anywhere on the terminal that's running this thing, and the status of the behavior tree is running, well, I have this local variable that I set to running to start with just to make the code easy. And what I have to do is I've got various ROS nodes that are doing interesting things. I have to give them some time to execute. That's what the spin sum does. This is, so far, it's just typically ROS stuff. And then here's the magic. I take that tree and ask it to tick the root node. And then, because I don't want this thing to go like a bat out of hell, I slow it down. And I slow it down to 15 ticks a second on this thing. And that, otherwise, when I'm looking at the tree and group, it disappears on 1/10 of a second. So I slow this thing down so I can actually see some interesting animation. And so that's the main code. So the only thing you need to write then are all these custom nodes that you talked about up here. I need to know about a move to pose and a say something node and a can see close wall, things like that. And there's two ways you write that kind of code. Let's take a look at can see or is a near wall available. So it's C++, so you usually write header file and then the body. Header file, standard include things that you do all the time. I put this thing in its own namespace because it just makes things easy. And since this is a simple condition code, I don't need to really write a class. I just need to have a function that corresponds to the condition. And I create using a macro that behavior tree provides a thing that says, if ever in the node, if ever in the behavior tree, you see a reference to a node called is near a wall, then I want you to use my code. And what does my code do? Well, here's the body. So the is near a wall. Well, this thing right now just always returns failure. What I had before, so here's a little debugging trick. What we had in here before is rather than actually fill in the body right now that goes and reads the LiDAR and checks to see if a wall is nearby, for my simulation, I want to create the behavior tree and not write any code that actually runs on the robot. I just want to see if the behavior tree looks like it'll run. So I have this little thing in here that says, if you've called this thing less than 20 times, return failure. And the 21st and later time, return success. So I have created in my mind a map about how many times I want a node to fail, succeed in that. And then I just, I have these lines like this in the original prototype code that just debugs the tree without ever talking to the robot. But for now, I just always return failure because I don't want to have to write this real code yet. I'm not at that point in my robot. But there are things I am at the point at. So for instance, there's the can see a close wall. So the can see a close wall seems like a simple thing, just like before, but the body is actually a little more complicated. So the can see a close wall goes and it calls this custom class I wrote that reads the line segments and builds an array of all the line segments that the robot discovered from the actual LiDAR. So I go get the class that I created and I ask it to get the line segments and it returns me a vector of this laser line class that I created. And then what I do is I say, go over every one of the laser lines on here. And for each laser line, if its distance is less than 6, I'm interested. It's a close wall that I see and I'll return success. But I put in some debugging code here. If it gets through this whole iteration, this whole for loop, it went over all the lines that the robot could see, and none of them are within 6 meters. In this case, it just returns running because, it's not really unsuccessful. It just hasn't found the line yet. You should come back and ask me again later. I might find a line later. So there's a move to pose. So if you're not writing simple little tests, the actions that you write have a common design pattern to them. So the common design pattern is you're going to have a constructor. So here's my move to pose. I've got a registration back in the main line that says if you ever see the words move to pose, I could have said, if you ever see the words flip flop, call my move to pose class. So there's a standard structure that you have to write, and it's kind of boilerplate. You'll see it in a second. And then there's 2 things that every node has to provide. One of them is this thing called provided ports, where you say if my node needs any ports, remember the input, output, in-out ports, you're going to tell it, the behavior tree, what those ports are and what kind of data do I want in them. And then you have to write a tick method. Every node has a tick method. So this extra thing here is extra code that I wrote here. So let's look at the body of this thing. So this is a little bit complicated on here. And what I'm trying to do is I think that I know where there is the closest wall that I should move to, and I want to move to it. So if we look first of all at the provided ports method, which should be down here. So this node takes a port called goal, and it's an input port. And I expect the data that's in the Blackboard to actually be one of these C++ serialized classes on the Blackboard. So when this tick node gets called, what it's going to do is, here's the tick method. So the behavior tree is going to call the node tick on this move to pose thing. And what it wants to know is it has to set up this transform. I know I'm going to want to do this transform from the LiDAR to the mapping coordinates out there. So I'm starting to set that up here. What I need to do is ask the behavior tree package to go and get me that goal value out of the Blackboard on here. So if it doesn't find one, I just barf. Otherwise, it will store the goal as one of these geometry messages things in the goal thing. So here I wait until the needed transform shows up. It's kind of what I did in the mainline program. Oh, I do it here because the transform might have gone away. And then I ask it to give me the transform from base link coordinates to map coordinates. So my goal is written in terms of base link frame of reference. And this transform will tell me how to translate that into a map frame of reference. And what I do here is I create a pose that corresponds to, what is it here? Oh, so the pose position is the thing I got from the goal. And I don't really care where the transform, what the orientation of the robot is. But then I say, go ahead and do that transform. Turn that thing from a base link pose into a map pose. Now that I've got the map pose, just for convenience, I pull out the X and Y coordinates of the map pose. I print a nice little log message about all the internal state. So if this doesn't work, I can figure out what went wrong. And then I'm going to create a message that I will send to the Nav2 stack. And the Nav2 stack wants to navigate to this pose goal thing. And so I create an object and I fill in the fields. It's using the frame ID. The current time is now. I want it to go to the X and Y transformed pose. I want the robot to point in the 0 rotation when it gets done. And then what I do is so this next thing here is the complicated stuff that talks to the Nav2 stack. And basically what this thing is going to do is it builds up a navigate to pose, action handle. It ends up calling the thing to move the robot. It says, I want to wait for the results of this thing. And down here, if the movement succeeded, well, I check whether or not the move worked or not. If it succeeded, I'm going to come down here and just say, yep, this move to pose worked. But when you tell it to go somewhere in the Nav2 stack, it can fail for lots of reasons. One thing is something could abort the attempt. And if it was aborted, I'm just going to return a failure down here after generated log. A request to go somewhere can also be canceled, in which case I'll just return failure. And if anything happens, I'll just return failure. So, if the Nav2 stack didn't move me to where I want, I just indicate that this thing failed, otherwise return success. So there's a lot more little tricky stuff I could show you in here, but you can go look at the GitHub and hopefully you can make sense out of some of this. I mean, there's one little tricky bit of code I wrote here. So NavStack, or the behavior tree.cpp, has this little cute piece of code they put in there that's not part of the normal behavior tree. It's a demo on how to write your own stuff. And I stole that code called say something. And in my behavior tree back here, I call a say something node. And what I want the say something node to do is tell me what it thinks the current goal is. Well, this say something, I don't want to get into too much stuff here, but basically it says, go and get from the blackboard the port called message, and it better be one of these, built-in geometry things here. And if it isn't, I generate a message here and barf the whole thing. Somebody's not generated a valid goal thing in the blackboard. Otherwise, I just print to the standard out, what is the goal? The goal is to be at X position, Y position, at this angle, and so forth, and just return. Okay. The point of this is you probably write some condition nodes. Condition nodes typically can be really small. Read the battery percentage. Maybe that's just looking at an I2C message or something like that. And then you return success or failure. Goals, condition nodes could be a little more complicated, like mine that relies on this background process that's constantly listening to the flood of line messages coming in. And it's saving the last line message, array of line messages that it saw. And my thing just says, and go capture the last one, or get the last one that you captured, and use that to figure out where the nearest wall is. You know, and then you write action nodes. Action nodes can be simple. Right now, using the Nav2 stack is hard because, you know, I had all that that code that I kind of skipped over that said, you know, it was creating a handle to the action, calling the action and checking to see if the thing is done and all of that. But that's because the Nav2 stack makes that hard. I think there's an easy way to do it. I've almost got it working, but I haven't quite. When I do, I'll change my GitHub to tell you how to do the easy way. So that's it.
All right. Thank you very much. Questions?
So
Yeah. So Mike, I got a
send
question.
check. Yeah.
So I guess I was struck by the amount of state that there is here for such a simple robot, and all the state is basically off in global space. So has that caused problems? Because I mean, when you're keeping track of state, right? You're keeping data about what the world was. It's not data about what the world is now. And so when you make decisions based on that, you're just making decisions based on what used to be, not what's necessarily
If
true.
you let this thing run, if you don't slow this thing down, like in the demo I have that wants to move the robot to the house or something,
Yeah.
it gets that behavior tree thousands of times a second.
Okay.
So
Okay. So
you may have,
here's one that's bugging
but
me.
it's,
Okay. You're keeping in the paper simulation, you're
Right.
keeping a stack of visited cells.
right.
Okay. And one of your behaviors is back up to previous cell.
Yes.
Okay.
Mhm.
So when you were in that cell to begin with, it was an open cell. Let's suppose that since then that cell has caught fire.
Good point. So
So that you were
my-
keeping track of what the world
does not-
used to be, not what it is now. Right?
that's right. You could write some more nodes in this behavior tree that handles that condition. It's not that hard.
But I have to do it. I mean, that's
We don't have to do much. So in the thing that's going to back up, I have a precondition that says that all neighboring cells have been visited. So I want to back up. I could add another precondition that says the cell that I want to back up to is still not blocked. If it is blocked, then I'm doomed. You know,
Yeah.
there isn't any place that I haven't been. Well, let's assume that I'm doomed. You know, there isn't any place that I haven't already explored near me, and I can't go back to where I came from. But the easy thing is just fail at that point and say, no, somebody's blocked my path. I can't do this. Or you could say, well, I can't back up, but maybe I can just wander off someplace I've already been. If there's still some unexplored cells in the house somewhere, my next strategy, if there isn't one I can move to that I haven't been to, and I can't back up, let's add another alternative strategy that just says, well, step on a cell I've already been on. Let's
yeah.
just keep on until I've exhausted all the time I gave my robot to play around.
Yeah. Okay. So. Anyway.
So the stale thing, it's only stale. So everything is stale in ROS. I mean, whenever you post a message, the messages have a timestamp in them. And even the SLAM stack has a parameter that says, how old can the data be that I can still rely on it to be useful? And so if you've got a moving robot, you get a sonar that occurred a tenth of a second ago, that sonar may not have any relevance at all to you anymore. And part of the SLAM configuration parameter, you say, only consider data that happened in the last 10 milliseconds. You know, and there may not be any good data, in which case SLAM just sits there and, you know, twiddles its thumb until some useful data comes along.
Any more questions?
I have a question. Why did you choose to use a stack for visited nodes when there are so many other alternative data structures that could have been used?
The stack is just capturing the path that the robot took to get to where it is. And that's because it makes it easy to go to the last place I was. Just pop off the stack and that'll be the coordinates of where I came from. And if that's all blocked, I can pop it off and go back to that cell and I'll get my way all the way back to the beginning, the first cell I started on. So it just seemed like, so that's not keeping track of the visited cells. That's done with an array.
Oh,
Two structures.
You've got another data structure, which is an array, and that's for some
Yes.
other purpose.
That array is keeping track of, has a cell been explored or does it contain an obstacle? So it really has three states, that it's an obstacle, that it's unexplored, or it's been explored. So I have an array that overlays all the area of my house, the map of my house, and every cell in that array corresponds to one of those states. And I have a separate stack, a separate structure, which is a stack that's used to capture the path that the robot has taken so far through that array.
I see. Now, when it comes time to dimension that array, you'd have to have some knowledge, I guess, about the overall size of the house. Otherwise,
yes and no. No, so
no.
the easy thing to do is to say that, yeah, I know my house is 30 feet by 60 feet. I'll create a 30 meter by 60. I'll create a 30 by 60 array to represent it. But as I was mentioning early on, you don't have to have a static array. I could just say that all I know is my house has one place the robot can sit on. And when the robot goes to a thing, it goes and scans all around it. And if it finds that, hey, there's other space that I didn't know about before, I'll just expand the array to hold that. And, you know, as it wanders around the house, it just keeps dynamically making the array bigger as needed. And it could be a sparse array, so it doesn't have to be a rectangular array. In fact, it doesn't have to be an array. You could use any of the graph forms, like a tree or something like that, to keep track of it. The modern SLAM algorithms, you know, the old SLAM algorithms in ROS 1, they used what was called a particle filter. And the particle filter, I don't know if this is relevant to what we're saying here, but a particle filter works by, you take a picture of where the robot is, the robot moves somewhere, you get another picture from all the sensors, the LiDARs. And what the particle filter does is it says, given the way the world looks now and the way the world looks before, let me make 2,000 guesses as to what the robot did to get here. And it says, well, if the robot went here, what should the world have looked like? And does that match the picture I saw? No, so that's not what the robot did. How about this guess? And it guesses typically several thousand times, and it's the one that best matches the world. But this is all on a sort of a grid representation. It divides your world up into little cells, and part of the configurations, you tell it, you know, how fine a cell array do you want? The new ROS 2 SLAM package doesn't do that at all. It uses a tree form representation of your house. It does some tree stuff that I haven't learned yet.
Would it be easier in terms of writing the actual source code for this behavior tree, or would it be more difficult if you used the kind of a tree structure instead of the array to represent all of the nodes that exist?
All of the nodes, you mean the nodes on the behavior tree?
Well, you said you're using an array for all.
To represent the map of the house. The array is measuring the map of the house, all the X, Y coordinates.
Right.
The tree is a real tree structure. So if you know what trees look like in computers.
I do.
Using, you know, just, yeah. So it's got a, you know, it's a data structure that pointed to the head and a list of its children. Yeah. But that's just to hold the behavior tree. What I was proposing here is that instead of overlaying your house with a grid of cells that are 1 meter on a side. You don't have to do that. And the array doesn't have to be fixed. You could use this dynamically expand. But another way to represent a sparse structure instead of an array or vector is you can use a tree representation. It's just one of those computer science things. If you have some idea about the density of the matrix or the space that you're trying to describe, there's, you know, a half a dozen different ways of describing it. It's kind of like you were saying, you really need to use a stack. No, there's a dozen ways you could do this.
All right. One more question.
Can I ask a quick question here? This is all in C++. Are there other language bindings for these libraries like Python or something else?
I'm not sure if behavior tree that simple. Someone wrote a binding, but you could certainly overlay it. I mean, most of Python is actually written in C++, and then there's a little.
I understand that. I'm just curious whether or not somebody had done a Python binding for this code base.
I do not know. However, there is another package. Remember, I said there's lots of behavior tree packages. I'm only going to talk about this one. There's another package called PyTrees, I think, that is a behavior tree written all in Python. It doesn't work quite the same as this one, but the concepts are all there, you know, sequences and fallbacks, and conditions.
Okay, good.
All right. Thank you very much, Mr. Mike. I know you put a ton of work into this and it was very thorough. Appreciate it very much. We do a ROS discussion group on Tuesdays if you'd like to join us. This concludes the official meeting. Chris, if you turn off the recording, that'd be great. I want to thank everybody for turning out. And again, especially you, Mr. Mike. We are now in random access mode. Just hang out until security comes and kicks us out. Thank you very much. Good to see you, Dave.